All right, so last time we briefly mentioned the problem of finding the maximum matching. Okay, so let's first review the definition of a matching. So because today we're going to design an algorithm that can find a maximum matching. Okay, so a matching is just a set of edges. Okay, so given a graph, you have to find a set of edges in the graph. And the only constraint is that these edges in the matching, they cannot touch each other, okay? In other words, they cannot share endpoint, right? So you can see that here we have two matchings. The first is the yellow one and the other is the green one. And if you consider the yellow matching, you can see that every one of them is like isolated, okay? They do not touch each other. So this is the definition of matching. And the problem is to find the largest matching. Okay, so we measure like the size of the matching by counting the number of edges. So if you only have two choices like this, we have the green matching and the yellow matching. And obviously the yellow one is larger because the yellow matching has 4 edges. Okay. And in this particular input, I think it's easy to see that the yellow matching is the maximum, okay? Because in this graph, we only have like we have 8. Yeah, we have 8 vertices, okay? So if you only have 8 vertices in the graph, the best you can do is to find 4 edges in the matching. So indeed, this yellow matching is the maximum matching, okay? So this is the goal of the problem, to find the largest matching in your graph, okay? So the last time when we discussed this problem, we consider, I would say, a simpler problem, so much simpler. So in this problem, all you have to do is find a maximal matching. So whenever you see maximal, it's like local maximum. So in the context of maximum matching, a maximal matching is a matching, like this green one, where you cannot add any more edges to it, okay? So consider this green matching. For example, you cannot add this edge, okay? Because if you add this edge, then these 2 edges will touch each other, okay? So that will violate the constraint for matching. Similarly, you cannot add this, or this, or this. So actually, you cannot add any more edge to this green matching. So this makes it a maximal matching, okay? So maximal matching is very easy to find. All you have to do is like you arbitrarily add an edge, okay? And then you remove all the like adjacent edges, okay? Edges adjacent to it, because you cannot pick it in the future, so we just remove it from the graph. And then we pick an arbitrary edge that is remaining on the graph again, and repeat the process, okay? So we just keep adding edges as long as they do not touch each other, okay? So that is maximal matching, okay? And so last time we showed that although maximal matching is not necessarily the largest one, okay? Yeah, because like this example here, the maximum matching we consider is the green matching, and it has a size of 3, not the largest one. But we show that actually they cannot be too far away from the optimal matching. The ratio between the maximal matching and the maximum matching is at most 2, okay? So this means, for example, you have a maximal matching of, say, size 10, okay? So you find a matching that has 10 edges, and it is a maximal matching. This slide tells you that the maximum matching can have at most 20 edges, okay? So the ratio is at most 2, okay? So in some contexts, we'll say that maximal matching is like a 2 approximation for the maximal matching problem. OK？ 所以我们上礼拜不是上礼拜，就之前大概就是讲这个 matching 的部分。OK？ 我们今天就会讲怎么样去找到最好的 matching。OK？ 怎么找到 maximal matching？ OK， 所以开始之前，大家对上次上课的内容有问题吗？所以我们今天会继续谈 matching 的部分。OK， 好 ，All right。All right, so today I'm going to start with like a general structure, the high-level idea to find maximum matching. Okay. Okay, so the key word here is M augmenting path. Okay, so the idea is that when, say, we start with a maximal matching, because maximal matching is easy to find, so we start with a maximal matching. Okay, but we know that maximal matching may not be the maximal matching, so we try to make it larger. Okay, but to make it larger or to enlarge a maximal matching, like this one, the green one, we cannot just add edges, right? You cannot add any edge to it. For example, you cannot add this edge because otherwise these two edges would touch, okay? So what we do is to find a spatial path, okay? So this spatial path is called M augmenting path. Augmenting means to make it larger, okay? So I'll just give you an example here, okay? So for example, let's consider this path. Okay? So I can use this path to find a larger matching, okay? So what's so special about this path? So first of all, this path is like alternating between edges in the green matching and edges not in the green matching. So for example, it starts with this edge, the edge between H and G, not in green matching, okay? The second edge in a green matching, the third one not in a green matching, fourth one in a green matching, last one not in a green matching, okay? And also you can see that the first and the last, or the endpoints of this path, it is not matched by the green matching, okay? In other words, this green matching, it does not touch the endpoints of this spatial path, okay? So basically what I've just mentioned are the definition or the property for this path, this spatial path, or the M augmenting path. Now, what I can do is that I can update the green matching along this spatial path, the M augmenting path. And the idea is very simple, okay? So I can just follow this path, and whenever the H is not in the green matching, I'll just add it to the matching, okay? So the new matching that I'm going to construct is that it will contain this HGH, okay, because it is not in the green matching. And the second one, this green H, well, I'm going to remove it from the green matching, okay? Because it's like I don't have any choice if I want to add this edge, okay? Because if I want to add this edge, then this edge, which is adjacent to this one, it cannot be in the matching anymore, all right? Because in matching, we cannot have like touching edges. So I'm going to remove the next one, all right? And follow using the same idea. So the third edge, which is not in the green matching, now this time I can add it to my matching. So the third one will be in the matching. The fourth one, because, well, it is in the green matching originally, so after the update, I'm going to remove it from the matching, all right? And the last one, I'm going to add it to the matching, okay? So the result will be like this, okay? I think I'm going to keep this one. So this is the original matching, and after the update, so this will be our new page, okay? So now you see that we've increased the size by 1, okay? And to do this, obviously we have to add some new edges to the matching. But also we have to remove some edges that were originally in the matching, okay? All right, so this is like the purpose of finding this M augmenting path, okay? So I think I'm going to first write down the definition. Okay, so before I define M augmenting path, I'm going to define a very similar related concept called M alternating path. Okay. So this is also an M alternating path. So the only constraint for M alternating path is that the edges must alternate between edges not in the matching and edges in the matching, okay? And whenever you want to discuss or talk about M augmenting path or M alternating path, you have to specify the matching that you are considering now. So for example, in our previous discussion, we only consider the green matching, okay? So it is our target. So in this case, M is the green matching, okay? So an M alternating path is just a path where the edges change between the edges in green matching and edges not in the green matching, okay? Okay, so perhaps I can give you another example here. So here, M is the green matching. And this path is an M alternating path. Okay. So obviously, any M augmenting path is M alternating. Okay, so it's like M alternating path is a broader set. Okay, and M augmenting path is like a special case for M alternating path. Okay. Okay. Any questions so far? 所以就基本上很简单，就是只要 H 它是就是交错出现 ，OK， 它是都是一个是在你的 M 里面，一个不在你的 M， 一个接着又在 M 里面，接着又不在，这样就是 M alternating，OK。Okay. Now, I mentioned that M augmenting path is like a special case for M alternating path. So the only difference is that for a path to be M augmenting path, the two endpoints, it cannot be matched by the green matching, or it cannot be matched by M. Okay, so this is the only difference. Okay, so we add some constraint to the endpoint of the path. Okay, and in graph theory, usually we use the phrase saturated and unsaturated. So a vertex V is saturated by M. Okay. So, for example, if we only consider the green matching now, okay, then this H vertex is not saturated by the green matching, okay? And on the contrary, this vertex D is saturated by the green matching because it is adjacent to this H, which is in the green matching, okay? I think I'm going to write out a definition again. Okay. So if it is not saturated, we call it unsaturated. Okay. So for example, A and H, these two verses are unsaturated. Okay, or they are not saturated by the green matching. Okay, so now we're ready to define M augmenting path. Okay, so first of all, it is an M alternating path. Okay. Okay. And we have to further add a constraint that the two endpoints of the path are not saturated by M. So as a current example, this one, this spatial path, is it M augmenting path? 所以这个 path 它是我们刚好说它是 M alternating， 但它是不是 M augmenting？ 它有没有符合这个上面的 augmenting path 的条件？所以有满足这个条件吗？问题是上面这个 path 它是不是 augmenting path？ 所以是吗？知道 augmenting path 的定义吗？ OK。So the only requirement for alternating path is that the edges must alternate between edges in M and edges not in M. Okay, so for example, you can start with an edge in M, but then the second edge must be some edge that is not in the matching M. And then the third one must be in the matching. Okay, so you can do this way, or you can start with an edge, you can start with a path where the first edge is not in the matching. Okay, then the second edge must be in the matching M. So that's alternating path. Right, so the difference between augmenting and alternating is that the two endpoints are the 端点 of the path, the first vertex and the last vertex. Right? So they cannot be saturated by M. And what does saturated mean? Saturated means that the verses, or the two verses here, they are like matched by the matching. Okay? So So this edge, this vertex edge, is not saturated by the green matching. Okay? And this, for example, like this vertex E, it is saturated by the green matching. Because it's like the matching matches E to D. All right? So we said that it is saturated. Okay. All right. So yeah, so that's a definition for augmenting path. Now back to this question, is it M augmenting path? Exactly, excellent. So this is not an M augmenting path, right? And the reason is precisely what she mentioned, that the first vertex, well, this one is already saturated, okay? So it cannot be M augmenting path, okay? Good. So if I add an edge like this, and I extend the path like this, then this will be an M augmenting path, because first of all, it is alternating. Second of all, the two M points are not saturated. Okay? Okay. Okay, so this is an augmenting path. Well, this is not an augmenting path. Okay. So I hope that you get the idea or the rationale behind M augmenting path. Okay. So the reason that we want that these two endpoints being unsaturated is that we want to find a larger matching. Okay. So in some sense, it's like we want to increase the number of vertices that are matched. We want to increase the number of vertices that can be saturated by the matching. So to do this, we have to start with some vertex that is not matched, okay, and make it saturated. So we want to start with 1, and because the number of saturated vertices, it must be an even number, okay? So to increase or to find a larger matching, you cannot just find one unsaturated vertex. You have to find 2 unsaturated vertices and try to, not necessarily just to match them. No, sometimes you have to match it to the other one and repeatedly until the last vertex is also matched by the matching. So you want to make, in short, you want to make sure that the 2 endpoints are not saturated so that you can find a larger matching, okay? And that's why I want to differentiate between alternating path and augmenting path. Okay. All right, so before I give you the algorithm to find augmenting path, okay, because we haven't mentioned how to find augmenting path. But before that, I want to at least make sure that we can, in some sense, always find an M augmenting path if the matching M is not maximum. Okay, because the idea is to find M, first find M augmenting path and find a larger matching and repeat the process. So we want to make sure that whenever the matching M we have is not the best, is not the maximum matching, I want to make sure that I can always find M augmenting path. Otherwise, I cannot use this algorithm to find M augmenting. I cannot use this idea, the idea of just find augmenting path and enlarge the matching. So I cannot use this idea if there's no M augmenting path. So I want to first convince you that we can always find M augmenting path, okay? Okay, so here the key point is to show that it exists, okay? Because if it does not exist, we'll never find it, okay? So we have to first, like, to show that it always exists, okay? And obviously, if M is like the maximum matching, it is the best one, you cannot find M augmenting path because finding M augmenting path implies that there's a larger matching. Okay, that's trivial. So if you have okay. So this is trivial, but this is not so trivial. Okay. Yeah. So anytime you have an M augmenting path, you can use it to find a larger matching. So if you have a M augmenting path, then the matching you have is definitely not the maximum matching. Okay. But we want to consider like the reverse direction. So if M is not the maximum matching, I can show you that there's always an M augmenting path, okay? OK， 所以等下我们要做的事情就是去说明说，如果你手上的 matching 不是最大的那一个，不是 maximum， 那一定有一个 augmenting path 等在那边等着你去发现 ，OK？ 你绝对不会说，手上的 matching 不是最大，但是也找不到 augmenting path。我们要说这是不可能的，只要你手上不是最好，就一定有 augmenting path，OK？ 所以这样我们刚刚的那个演算法才会 work，OK？ Okay, so we're going to use M star to denote the maximum matching. So if we consider this example, then M is like the green matching, and M star is the maximum matching. Okay. And we want to show you that I can use these two matchings to build an M augmenting path. Okay. So now you can see that once again we transform a proof into like an algorithm design problem. Okay, so this is the proof, but when we think about this proof, we can make it like an algorithm design problem. So given two matchings, so this is not a maximum matching, and this is a maximum matching. So how to like design an efficient algorithm to find an M augmenting path using these two matchings. 所以有人可以看得出来，给你两个 matching， 第一个是你手上有的，不是最好的那一个，然后我同时也给你一个最好的 matching， 那你要怎么利用这两个 matching 去建一个 augmenting path 出来？那如果你可以把这个建法类似把它写出来，那基本上你就可以证明说一定有 augmenting path。Right? So the hint is that we can only use the edges in the two matches. Okay, so you can use the yellow matching, and you can use the yellow edges, and you can also use the green edges. Okay, and the goal is to create an M augmenting path. Okay. So first of all, you can notice that for some edges, they can be in the green one and the yellow one. Okay. So actually, we're going to ignore this kind of edges because, well, at least I don't know how to use these edges in the M augmenting path. Okay. So in the algorithm, we will just remove or ignore edges in M intersect M star, okay? So if some edge appears in both matchings, I'm not going to use it in my M augmenting path, okay? Because I know that this M augmenting path, it must look like this, okay? Start with some yellow edge, followed by a green one, followed by a yellow one. Sorry. Okay. So it must be in this form, okay? We start with some unsaturated vertex and using some edge in M star, okay? So recall that M star is the yellow matching. Okay? So if this path has this form, I'm not going to use any kind of these edges. Okay? So if it is both M and M star, then I cannot use this kind of edges. Okay? So I'm going to just ignore this kind of edges. Okay? And then consider the other edges in M and M star. Okay? So next, let's just consider the union. Okay? But since we exclude or we ignore this kind of intersection, we're going to exclude edges that appear both in the green one and the yellow one.所以到目前为止，我们就是很单纯，我们就是考虑 M 跟 M star， 然后我们刚刚说的就是那种如果有共用的，那我们就不会用，就直接把它删掉。OK。So actually, there's a name for this kind of operation. It is called exclusive or XOR. Okay. So the exclusive OR of two sets is just the union minus the intersection. Okay, so here we just consider the exclusive OR of M and M star. Okay. Okay, so let me give you a very simple warm-up question. So if I want to count the degree of a vertex, and I just consider the exclusive OR, okay, of these two matches, then what is the largest degree I can have if I only consider edges in the exclusive OR? 所以如果今天只考虑 match 里面的 edge， 然后我现在问的问题是，我要看里面的 vertex 的 degree， 那这个 vertex 的 degree 最多可以到多少？然后这边再次强调，我只考虑 M 跟 M star 里面的边而已。Okay. Okay, perhaps let's consider even simpler question. So if I only consider a matching, okay? So you can imagine that the graph you have is a matching, okay? Then what is the maximum degree of a vertex in the graph? 如果我的这整个 graph 它本身就是一个 matching， 那这个 vertex 的 degree 最大可以到多少？ So if the graph itself is a matching, then the graph will look like this, okay? Then what is the maximum degree? E1, okay, because any vertex is adjacent to at most one edge. All right. 所以如果今天你就是只有一个 matching， 那 maximum degree 就会是1。那有一些点它可能没有被 match 到，譬如说像这个点。OK， 所以像这个点它的 degree 就是0，但是对这个点或这个点或这个点，它们的 degree 就是1。 所以 maximum degree 就会是1。Okay. Now this is just one matching. In our proof, we have to consider 2 matchings. Okay. So if I have a second matching, like this, then what is the maximum degree? degree 是吧？如果有2个 matching 的话。Right, because we have 2 matchings, and if only consider the green one, the degree is at most 1, and if only consider the yellow one, the degree is at most 1. So combining them, you get 2. Okay. Okay. So in short, so you can also consider this. This M and M star. So once again, we only consider edges in M and M star. So edges like this is not considered here. Okay. So if we ignore these edges which is not in M and not in M star, okay, and we only consider edges, the yellow one and the green one, then the degree is at most 2, okay, because it's a matching, so every vertex is adjacent to at most 1 yellow edge and at most 1 green edge, which makes it at most 2, okay? Right, so, yeah, at most 2, okay? All right, so now we've obtained some property about this M and M star, okay? So next, during the break, because I know that the bell just rang, so you can think, so if I know that the graph has a maximum degree of 2, then what would the graph look like? Okay, if every vertex has at most 2 neighbors, then what are some possibilities for the components in the graph? Okay, 所以大家下课的时候可以想一下，如果每一个点 degree 都是2，最多是2 ，OK， 所以有可能有一些点 degree 是1，这是有可能 ，OK。那这样的话，那个 graph 它会是什么样的 graph？OK， Right, so let's take a break. Okay, before we start our discussion on M-organic path, I have a couple of announcements to make. So first of all, today I'm going to upload the first assignment to Moodle, okay? So you have 1 week to finish an assignment and upload it to Moodle, okay? So that's the first one. Okay? So you have 1 week, okay? Because next week we're going to discuss the solutions for the first assignment, okay? And we'll have our midterm the next week. The week after the next week, okay? Okay, so I believe it's April 24th. Yep, okay. So we'll have our midterm in 2 weeks, okay? And it's an open book exam, but you cannot use the internet, okay? You can bring any textbook, any notes, okay? Any slides, as long as you print it out, okay? You cannot bring or use any like smartphone, electronic devices, no, okay? So only hard copies. Okay? All right, so back to M-organic path, okay? So now we consider a graph such that the maximum degree is at most 2, okay? Then what would the graph or what would the components look like if every vertex has at most 2 neighbors?所以如果一个 graph 里面每一个点它都只有2个邻居，那这个图里面的 component 会画起来会长怎么样？最多只有2个邻居。So actually there are only 2 possibilities. 所以有什么可能？如果每个点最多只有2个邻居？ A line, or in graph theory, I think you refer to path. Okay, path, okay. So it can be a path or what? So a path is like this, okay? So this is a path, okay? Exactly, cycle. Okay? And so there's really no other choices, okay? So because you start with an edge and followed by another edge, then immediately you know that I cannot add any more edge to this middle vertex. Because if I add the third edge to this vertex, then the maximum degree would exceed 2, okay? So if I want to add any more edges to this component, I can only add it to the left or the right, okay? Or just connecting these 2, okay? So the only 2 possible components I can have are path or cycles, okay? Okay, so if it is a path, I claim that it must be an alternating path. So why? Because I only consider edges from these two matchings. Okay? Since they are both matchings, I cannot have two consecutive edges that are from the same matching. No, I cannot have yellow, yellow like this. No. Okay? It must be yellow, green, yellow, green, yellow, green. Okay? Or green, yellow, green, yellow. So it must be an alternating path. Okay? So similarly, if it's a cycle, it must be an alternating cycle. I know I didn't define alternating cycle, but I think it's easy to guess that alternating cycle is a cycle where the edges of the cycle alternates between edges in M and edges not in M. So yellow, green, yellow, green, yellow, green. Okay? So alternating cycle. Okay? Moreover, I claim that the length or the number of edges on this cycle, it must be an even number. It cannot be an odd number. So can you see why? So for example, it cannot be an alternating triangle. 可以看得出来为什么这个不可能吗？有没有可能 M exclusive M star 里面有一个三角形？有可能吗 ？OK， 为什么不可能？我给他直觉，为什么？有更具体的理由。So once again, I want to stress a very beautiful idea in graph theory is that you can always try some examples. Okay? So in this cycle, okay, if I want to convince yourself that this is not possible, all you have to do is to, because it is from M and M star, so green and yellow. So just try it, okay? So for example, I color this green. Therefore, because it's alternating, so the next one must be in yellow. So now, do you see the problem? So what is the problem? So 这样不可能的原因在哪里 ？Sorry。啊哈，按他选黄色也没有交错。Exactly. So if the length of the cycle is an odd number, then it cannot be an M alternating cycle. So that's a reason. Okay. So it's an even M alternating cycle. Okay. So if it's an even cycle and it's alternating, then it must be the case that the green edges and the yellow edges, they contribute the same number of edges in the cycle. Okay? In other words, in this cycle, we have the same number of edges from the green one and from the yellow one. OK， 所以既然它是偶数的边的个数，然后它要是交错出现，所以绿色的 跟黄色的边的个数一定会是一样的。OK。And recall that the goal is to find an m augmenting path. Okay, an m augmenting path it must be from this kind of components, path. Right? So it cannot be from a cycle. Okay, so next, okay. So once again, we can compute the length of a path. So it can be an even path or it can be an odd path, okay? But recall that m star is bigger than m, okay? So if m star is bigger than m, then there must be some component in which m star has more edges than m, okay? Okay. So we consider the exclusive of m and m star, and we know that there are only two possible components, path or cycle. And we further establish the property that if it's a cycle, then actually m and m star, they have the same number of edges, okay? So if there's one component in which m star has more edges than m, then the component cannot be a cycle, right? Because if it's a cycle, then actually m and m star, they have the same number of edges, okay? So if it cannot be a cycle, then the component must be an m alternating path. Moreover, in this alternating path, m star has more edges. Okay? In other words, we have the number of yellow edges is greater than the number of green edges. Okay? So we have more yellow edges, okay? And less green edges. So the graph or the path must look like this, okay? Okay. Now, is it an m augmenting path? Now, I know that it is an m alternating path. I also know that in this path, the first and last edge is not from M. Okay? But the definition for augmenting path is that the first and the last endpoint are not saturated by M. Okay, so that's a definition. So how to argue that the two endpoints, they cannot be saturated by the green matching? 所以我们现在有的是，我们有一个 path，alternating path，OK， 它是交错出现，然后这个交错出现的这个 path 里面的第一个 edge， 它是黄色的 edge， 它不是绿色的 ，OK， 最后一个 edge 也是一样，它不是绿色，它是黄色的 ，OK， 但是这个不是那么完全贴切 augmenting path 的定义，因为 augmenting path 它的定义是第一个跟最后一个 endpoint， 它必须要没有被 green edge saturate，OK， 所以我要怎么去说明说这两个点，它事实上一定没有被 green edge saturate， 没有被它 match。所以有没有可能这个点它事实上有被 green edge match？ 比如说它事实上这边还有一个绿色的 edge， 那就基本上就不太可能，因为如果是这边还有一个 green edge 的话，那这个我画出来的这就不是一个完整的 component，OK？那或者你可能想说，那会不会是这边是那个 exclusive or 去掉的那一个？所以换句话说，就这边它同时是绿色也是黄色，因为我们刚刚说我们已经把它丢掉了，因为这个是我们不会考虑的。当然也不可能说这里有绿色也有黄色，因为如果这里有绿色也有黄色的话，它就会违反黄色是 matching 的概念。OK， 所以简单来讲，就这两个，它一定不会被绿色的 saturate。Okay. Okay. So as a result, this component itself is an M augmenting path. Okay. So that's a proof. So the idea is that if you have a matching that is not maximum, then you consider the exclusive of this matching and the maximum matching. Okay, and there must be one component such that in this component we have more yellow edges than green edges. Okay. So that component itself is an M augmenting path. Okay. Right. So this shows that whenever the matching you have is not the best, there must be some augmenting path waiting to be discovered. Okay. 所以对这个 proof 有问题吗？所以刚刚我们的目的就只是说，如果我们的 matching 不是最好的，那我保证一定会有一个 augmenting path 在那边等着你，等着被你的演算法发现。OK。那这边我觉得整个最关键的就是刚刚这个讨论，就是因为我们看的是两个 matching 的 union 或 exclusive or， 所以他们的 degree 最多就是2，每一个点的邻居最多就2个。所以如果最多邻居就是2个，你就会有只有可能是 path 或者是 cycle，OK，、然后如果是 cycle 的话，一定会是 even， 不会是奇数的状况。所以如果是 even 的话，那就代表m 跟 m star 它们贡献的 edge 数会是一样。所以换句话说，一定会有一个 component，OK，、因为 m star 比较大嘛，所以铁定会有一个 component m star 会比较多的 edge，OK，、那一个 component 就一定不是 cycle， 就一定会是 path，OK，、所以这个演算法整个分析的关键。Okay, so now time to find augmenting path, okay? So we're going to design an algorithm. Okay, so the algorithm we will discuss next can only be applied to bipartite graphs, okay? Because if you want to find augmenting path in general graphs, then it's kind of complicated. So in this course, we only consider the algorithm for bipartite graphs, okay? So first of all, let me define bipartite graphs. Before I finish the definition, let me first draw an example. So I think once you see the example, you know the idea of bipartite graphs. Okay, so that's a bipartite graph. Okay, and basically, if a graph is a bipartite graph, then you can divide the vertex set into two sets. Okay, and all the edges must be between these two sets. Okay, you cannot have edges within like, so let me call this V1, the upper set, and this is V2. Okay, so all the edges are between V1 and V2. Okay, so you cannot have edges connecting two vertices in V1. Okay, this is not allowed. Okay. So this triangle, is it a bipartite graph? In other words, can you find a way to partition the vertex set or find a way to partition these three vertex so that, so you can divide it into V1 and V2 such that all the edges are between V1 and V2. 所以有没有可能找到一个 partition 的方法 ，partition 成 V1 跟 V2， 然后 V1 之间都没有 edge，V2 之间也没有 edge， 有没有可能？如果你的图长这样的话。有可能吗？不确定。So basically, all you have to do is to try one possible partition because it is like symmetry. Okay, it's a cycle. Okay, and so I can divide it like this. Okay. So this vertex is in V1 and these two are in V2. So immediately you see that this is not a bipolar graph because there's an edge between two vertices in V2. Okay, so yep, so this is not a bipolar graph. Okay. How about this? Is it a bipolar graph? Yes. Okay. So to partition it, you can do this. Okay. So the top and the bottom vertices, they are in V1. Okay. The two vertices in the middle, they are in V2. Okay. So you can see that all the edges, they have one endpoint in V1 and the other endpoint in V2. So that's, I'll say, a valid bipartition. Okay. Okay. So anyway, next we will focus on graphs like this, where you can divide it into two sets, and all edges are between these two sets. So that's a bipolar graph. Okay. Perhaps I should add M. Okay. So this is to stress that whenever you want to find augmenting path, you must have a matching. Okay. You first have a matching, and then you can find an M augmenting path with respect to the matching. So let me first give you an example. Okay, so this is the bipolar graph. Okay. Next, let me draw the matching. Okay, so this is the matching. All right, so the goal is to find an M augmenting path. M augmenting path. Okay. So the algorithm is like a BFS search. Okay, so because we know that an M augmenting path must start with an unsaturated vertex. Okay, so we start from some unsaturated vertex in V1. Okay, and for example, let's try this one. Okay, so we start with this vertex, and we'll extend the path. Okay, obviously we have to extend it following the M alternating path logic, And we want to find an M alternating path where the other endpoints is like this one, or this one, or this one, because these three are not saturated, okay? So we start from some unsaturated vertex in the top and want to finish at some vertex, some unsaturated vertex in the bottom, okay? And all the edges in the middle, they must alternate between edges not in the matching, followed by edges in the matching. Okay, so for example, I can use like this edge to reach this vertex, and then I have no choice but to follow this green edge because it must be an M alternating path. And then after I reach this, I can, for example, like use this edge, okay, to reach this one, and use this, and then use this. Now I've reached an unsaturated vertex in V2. So that's job done, okay? Okay, but all I just do is like visually just eyeball this picture and figure out the augmenting path. So next I want to give you like an algorithm, okay? But really the idea is just to keep extending the path, okay? Until we reach some unsaturated vertex. And we'll do this in like a BFS search. Okay. Okay, so a few variables that I'm going to use. So actually, I'm going to use these variables for other purposes, like to analyze the algorithm. Okay. And to prove some property, okay? So these notations or variables, they are not just only for the algorithm. No, I'm going to use it later in the proof, okay? So first of all, U, okay? So U is the set of unsaturated vertices in M. Okay, so for example, this is in U, this is in U, this is in U, and this is in U, okay? Because those vertices are not saturated by the green matching, okay? And because I want to extend this path, so I want to trace the vertices that I can reach using alternating path, okay? So I'm going to use S to denote the set of, this is not in M, this is in V1, okay? Okay. So S is the set of vertices in V1. Sorry. In V1, that can be reached from U using M alternating path. So which vertices are in S? So initially, all the vertices in U are in S because definitely I can reach these 4 vertices from U, and I don't have to use any edges, okay? So initially, all these 4 vertices are in S. And so for example, this vertex is in is in S because I can use this path. First this edge, followed by this green edge to reach this vertex. So this is in S. Okay. And after I reach this vertex, I can use this edge to reach this one, and then I can reach this one. So this is also in S. Okay. So this is just for the purpose of explaining the definition of S. So later in the algorithm, we will construct this S, okay, in a systematic way. So this is S, and T is defined in a similar way, but now it's the vertices in the bottom, okay? Okay, so for example, this is in T. Okay, and so actually I think this is also in S because I can use this path. No, sorry. Okay, so I can use this, this path to reach this vertex, so this one is also in S. So let me add one more vertex to S, okay? Okay, but back to T, okay? So this means we can add this vertex to T because we can use this sparkling path to reach this vertex, which makes it in T, okay? And next, okay? So this is also in T because after I reach this vertex, I can use this one, okay? So this is in T, and this is also in T, okay? Once again, don't worry if you cannot see how to figure out which vertices are in T. So this is just examples, okay? I'm going to give you an algorithm to construct S and T. But the goal is that we want to construct S and T such that we know which vertices in V1 that is reachable from U, and which vertices in V2 is reachable from U, okay? And we must use alternating path to reach these vertices, okay? And if you want to find augmenting path, it's like you want to reach some vertex in T that is not saturated, okay, like this, okay? So let me draw the augmenting path that we just discovered. I think it's this, okay? So this one is not in the matching, in the matching, not in the matching, in the matching, not in the matching. And the two endpoints, they are not saturated by the matching M. So it's an M augmenting path, okay? And by the way, let me draw the graph or the matching after we update, after we like enlarge it, okay? So the new, okay, I think I use a slightly different color. So this one is added to the matching, this one is removed, this one is added to the matching, this one is removed, and this is in the matching. Okay? So this will be the new matching. So this is construct based on the original matching M and M augmenting path. Okay. So I think I haven't written down the algorithm to construct the larger matching based on augmenting path. So I think I'll do this here. Okay. But that it's quite easy, okay? So input, you have a matching N, M and an M augmenting path. So I'm going to use this notation EP, okay? So this is the set of edges in P, okay? So we will just return the exclusive OR of M and edges in P, okay? For example, okay, so here the dark green edges are the edges in M, and this path is the M augmenting path, okay? So by taking the exclusive OR, I will keep this, okay? Because exclusive OR is like take the union, okay? But the only difference is that I'm going to remove any common edges, okay? If this edge is in M and P, then I'm going to remove it, okay? Otherwise, I'm going to keep it. So this one, I'll keep it because it only appears in this path. And this one, I'm going to remove it because it appears in both the matching and the path, okay? So similarly, I'm going to keep this one, remove this one, keep this one, remove this one, and I'm going to keep this one, okay? So this is what I just did here, okay? So we will keep this one, remove this one, keep, remove, keep. Keep this one, and keep this one. Okay. All right. 有问题吗？所以刚刚讲的是，这刚刚已经讲在，我记得在第一节课就讲过，就是要怎么让 matching 变大。如果你有一个 augmenting path，所以刚刚只是 稍微比较严谨的把它写出来，但严谨其实也很简单，就是取 exclusive for，OK？所以你看到 exclusive for 在两个地方都有派上用场。第一个是我们在看 M 跟 M star 的 exclusive for， 那个目的是要是说一定会有 augmenting path，OK？那你有了 augmenting path 之后，你要怎么让本来的 matching M 变大？一样就去看 exclusive for，OK？然后我们刚刚有去定义这三个 set， 这三个 set 会跟着我们大概2-3个礼拜，甚至更长 ，OK？ 特别是这个 S 跟 T，OK？所以这边我要讲了，再讲一次，就是 S， 就是那些你可以从 U 出发然后抵达的那些点，而且 S 都是在 V1。那 U 是什么 ？U 就是那些没有被 saturate 的点，因为这些是我们去建 augmenting path 的起点。因为 augmenting path 它起点一定要是没有被 saturate，OK？然后我们就会去记录说，哪一些点它可以被我走到 ，OK？所以如果那个可以被走到的点，它是在 V1 的，那就在 S； 那一些可以被走到的点，如果是在 V2， 那就在 T，OK？然后只是因为我们这边是 augmenting path， 所以我们所谓的走到，我们用的 path 一定是要用 alternating path，OK？所以这是 S 跟 T 的定义。好，那我们先休息一下，我们等一下就回来讲那个演算法，一个比较有系统的去找 augmenting path 的演算法会长怎么样 ？OK， 好，我们先下课。 All right, so let's design an algorithm to construct augmenting path. Okay, so the algorithm will proceed in rounds. So we have round 1, round 2, round 3, and so on and so forth. So in each round, what we will do is that we will pick a vertex in S, okay? For example, like this one. And then we'll extend the M alternating path. So to extend the alternating path, we'll do 2 steps. So first of all, we are going to we're going to use some edges not in the matching to go down, okay? Because, for example, you can observe that the reason that we can reach this vertex is like this. We can use first this edge not in the matching, followed by this in the matching, okay? So the next edge must be, if I want to go down to V2, it must be some edges not in the matching, okay? So we use these 2 edges to reach these 2. So based on our definition, this will be in T, okay? And then we extend the path 1 edge further. So when we reach this vertex, we want to check whether we can further extend it. So that when we want to go up back to V1, we must use some edge in the matching, okay? Okay, so this makes it makes this 2 vertex in S. Okay, so this is 1 round. So in every round, we just pick a vertex in S. We go down using some edges not in the matching, and then we go up using some edges in the matching. Okay, and when we go down. When we go down and reach some vertices in V2, we want to first check whether they are saturated or not. If it is not saturated, then we're done. So for example, when say some in round 5, okay, we start from this vertex S, and we go down using some edges not in the matching. So we're going to reach this vertex, and this is not saturated. So we know that we found an augmenting path, okay? And because we also want to output the augmenting path, so for every vertex, we are going to keep track of its parent or its previous vertex or like its parent, okay? So for example, we're going to set the parent of this vertex to this guy because we use this edge to reach this vertex from this vertex, okay? So the parent of this vertex is this guy, okay? And similarly, the parent of this vertex is this guy. So we use this parent attribute to construct the path. Okay. All right. So I think before I write down the whole algorithm, I'm going to first apply the algorithm and show you how the algorithm works. So initially we have to find all the vertices in U. Okay. And this is simple, okay? You just check every vertex in V1 and see if it is adjacent to some edges in the matching. So this step is easy, okay? And as I mentioned earlier, these vertices are also in S, okay? So this, until now, these are all initialization steps, okay? Next, we're going to start our first round, okay? So in every round, we will pick some vertex in S, okay? So let's pick this one, okay? And the first step is always to go down, okay? Using some edge that is not in the matching, okay? So we can reach this vertex, and this will be in T, okay? So I think I'll give them some names. Okay. So in the first one, we use this edge to reach this vertex, J. So the parent of J will be A, okay? And we can then go up, okay, using some edge in the matching. So you have to be careful here because here we have multiple choices, okay? So you can choose this one, or this one. But since this is alternating path, we can only use this edge that is in the matching, okay? So we have to use this edge, okay? So this means this vertex E is also in S, okay? I think I'm going to just write PS, okay? Sorry, PE. So the parent of E is A, okay? And that's it, that's the first round, okay? So in the second round, we can choose any vertex here among these 4 vertices in S, okay? We don't need to consider this again, okay? Only need to consider these 4 vertices. So for example, we can, let's choose, yeah, how about this, okay? Just choose E, okay? Okay, we choose this guy, okay? And again, we first go down, okay? Using edges not in the matching. So we can reach K and L, okay? So K and L, they are in T, okay? And by the way, when we reach some vertices in V2, we want to check whether they are saturated or not. So in this case, both of them are saturated, which means the algorithm is cannot finish now, okay? We have to further extend the Okanagan path, okay? But the parent of K is E, and the parent of L is also E, okay? Because we use this one and this one, okay? So that's why I can add this K and L to T, okay, and set the parents to E. Okay. Okay, and then I can go up. And when I go up, I must use edges in the matching. Okay. So this is in S, and this is also in S. Okay. So the parent of C is K, and the parent of G is L. Okay. Okay, now this finishes the second round. Okay.
What was the parents of E?
The parent of E, A, because the reason we can reach E is, oh, it should be J, right? Is that your problem?
Yeah.
Yeah, thank you. So the parent of E should be J. Sorry. Yeah, the parent of E is J, and the parent of J is A. Yeah, thank you. Okay, good. Okay, so I think I'm going to erase this. So now we've checked A, E, okay. So next, let's check G. Okay. So there's no particular order that we must follow when we pick vertices in S. Okay. So you can do it like BFS, or you can do it like DFS. Okay. So actually, there's no constraint. Okay. But obviously, if you want to find a shorter augmenting path, you may want to follow like BFS to make sure that the augmenting path is short. Okay. But anyway, that's because I know that if I choose G next, then I can finish the algorithm earlier. So I'm going to choose G. Okay. All right. So in each round, we always first go down. Okay. And in this case, we reach this vertex M. So the parent of M is G. Okay. Now, whenever I reach some vertex in V2, I have to check whether it is saturated or not. So in this case, it is not saturated. This means we found augmenting path. Okay. So to reconstruct the augmenting path, I can use this parent attribute to backtrack and reconstruct the whole path. So I know that to reach M, I have to use vertex G, and to reach G, I know that I have to use vertex L, and to reach L, I have to use vertex E, and to reach E, I have to use vertex J, and to reach J, I have to use vertex A. Then I can backtrack and reconstruct the whole augmenting path. Okay? So that's basically the whole algorithm. Okay? So I think for completeness, I'm going to write down the algorithm to make sure that we're on the same page. Okay, so this is the two steps we do when we before we start the first round. Okay. So U is initially all the saturated vertices in V1, and S is initially just a set of U. Okay. So in every round, first we pick a vertex in S, okay? Let's call it V. Okay. So also I don't want to check the same vertex twice, okay? So I only pick the vertex that I haven't checked before, okay? Okay. So V is the vertex in V1, and always we first go down, okay? So go down means I want to find the neighbors of V, and when I go down, I can only use edges not in the matching, okay? Okay, so I have to check all the possible neighbors, but these neighbors, the edges cannot be in the matching M. Okay. So we're going to set the parent of U to be V. Okay. And then you can add T, add U to T. Okay. So actually, if you only want to like output the augmenting path, you don't need this T. Okay. So actually, this T is really for the proof that we're going to use. Okay, in the future. Okay, but yeah, I'm going to leave it in the algorithm. So if this vertex U is not saturated, then return the augmenting path. Here I write this in the form of a function. So this is aug path, and the input is U. So what this function does is that it uses the parent field to backtrack and reconstruct the whole path. Okay. Okay. Okay, so I think I have to draw a picture. So we have this vertex V, and then we go down to reach this vertex U, okay? And if U is saturated, then we can go up again. And I'm going to call this vertex W, okay? So first go down, and then when we go up, we must use some edges in the matching, and I call this endpoint W, okay? So W, okay? So W is a vertex that is matched to U in the matching M, okay? So I just set the parent of W to U, and add W to S, okay? And that's it. So let me stress that this is not in M, and this is in M. Okay. Okay. And a small remark for the first step, when we pick a vertex, we say that we don't want to pick a vertex twice, okay? So if you observe that all the vertices have been picked before, this means there's no way you can further extend the path. So in that case, you just return no, there's no augmented path or empty set or null. So anything to represent that there's no augmenting path, okay? So this is possible because if the matching M that you're considering now is actually the maximum matching, then you cannot find an augmenting path, okay? So in that case, you're going to check all the vertices in S, and you're not going to find any augmenting path, okay? OK， 所以刚刚这边我们只是把我们前面的 example 比较具体的写出来，说基本上每一个回合就是先往下再往上，然后往下的时候一定就是用不在 matching 的边，往上就一定是用 matching 的边，然后我们在每一个 round 一开始去选那个 vertex 的时候，那个一定是我们没有挑过的 ，OK？ 所以如果你发现每一个 vertex 都被挑过了，那你就直接 output 说没有 augmented path，OK？ 那我刚刚说这绝对是有可能，因为譬如说你给这个演算法的 input 的 matching 如果是就已经是 maximum matching， 那你绝对找不到 augmented path，OK？ 好，但是如果它不是 augmented path，这个演算法基本上就一定可以找到augmenting path，OK？ 因为它基本上就暴力去试所有各式各样的可能性。Okay. So this is the algorithm to find augmenting path. So to find the maximum matching, you just repeat the algorithm, okay? So first you compute a maximum matching, for example. So compute a maximum matching, find M augmenting path and use this algorithm to enlarge the matching, and then find augmenting path, and then apply this algorithm to enlarge the matching until the M augmenting path algorithm cannot return any augmenting path. And that's, at that moment, the matching you have will be a maximum matching, okay? Okay, so this is the algorithm. Start with some maximum matching, find augmenting path. If the algorithm cannot find augmenting path, we just return the current matching. Otherwise, if there's a path, augmenting path, we take the exclusive OR and repeat the process. Okay. Okay, so I said that the algorithm, it's kind of brute force. Try all the possible alternating paths, okay? So in some sense, the algorithm is correct. That is, if the algorithm returns nothing, then really there's no augmenting path, okay? But I want to have a more like straightforward proof or a certificate to show that the algorithm, when it cannot output any augmenting path, the algorithm really is correct, and the matching you have is really the maximum matching, okay? So in other words, how to show that a matching is indeed maximum. Okay, so given a matching, how to convince others that this is really the maximum matching you can have. Okay. Sure, you can say that I've applied a previous algorithm to try to find augmenting path, but it fails. Yeah, that's one way to convince others. But perhaps your algorithm has some bugs. Okay, or you may, I don't know. But anyway, the algorithm itself is not the most convincing way to show that it is maximal. Okay, we want to have a certificate, a more straightforward way to show that it is maximal. Okay. So for example, if you consider this yellow matching, there's a very simple, very straightforward way of convincing others that this yellow matching is indeed the maximum matching, because the argument we had is that we have 8 vertices, okay? So if your matching already saturates all the matchings, all the vertices, then this is the best, okay? So in short, if your matching can saturate all the vertices, then obviously this is the maximum matching, okay? But this may not be the case for all graphs, okay? Because for some graphs, the maximum matching cannot saturate all the vertices, okay? So for example, like this one, okay? So this is the whole graph. Then the maximum matching is just like this, okay? So you can only saturate 2 of them, okay? Not every vertex in the graph, okay? Yeah, so how to show that this is a particular matching is really the best? Okay, so to this end, we're going to introduce a very different problem. I think it's hard to see the relationship between the problem that I'm going to introduce next and the matching problem, okay? Yeah, but I'm just first define the problem and explain to you that why these 2 problems are related, okay? Why it helps to study the problem, okay? So the concept that we're going to define is called vertex cover. Okay, so that's a definition. Before I explain it, let me first give you an example. Okay. So in the problem of vertex cover, we don't choose edges, okay? We choose vertices. Okay. So the basic idea is to find vertices to cover every edge. So what do I mean by cover every edge? So an edge is covered, for example, like this one, it is covered if at least one of the endpoints is chosen, okay? So this one is covered, okay? This edge is also covered because we choose this vertex. This edge is covered because we choose this edge. This one is also covered. So actually you can check every edge in the graph. At least one of its endpoints is the chosen vertex. Okay? So these 3 vertices, they form a vertex cover. Okay? 所以 vertex cover 就很简单，就是选 vertex， 然后 vertex 要可以 cover 所有的 edge。OK？ cover 的意思就是你有我们说一个边被 cover 就代表说那个边的其中一个端点有被你选中。OK？ So the problem we're interested in is to find the minimum vertex cover. Okay? Yep. So this is the problem to find the smallest vertex cover. Okay. Okay. Okay, so let's try to find the minimum vertex cover, the smallest vertex cover to cover every edge. So how many vertices that you can choose and to cover every edge in the graph? That's the smallest way, or the smallest number of vertices, the fewest vertices you can choose to cover every edge. So 如果你要上面有5个边嘛，所以如果你要 cover 这5个边，你最少要用几个点？要选几个点？2，所以是哪2个点？OK。Right. So for this graph, you can use just 2 vertices to cover every edge. Okay. Now, what is the size of the maximum matching? Can you find a matching of size 3? Okay. So for this graph, the best you can do is to choose just 2 edges in your matching. Okay? So it seems like these 2 sets, they have the same size. Okay? But before we show that, let me first give you a simpler relationship. Okay? So C is any vertex cover. Not necessarily the minimum vertex cover, any vertex cover. Okay? So for example, you can choose all the vertices. This will be a vertex cover. Okay? And M is any matching. And once again, this is any matching, not necessarily the maximum matching. Okay? So for example, you can choose just 1 edge. So 1 edge itself is a matching. Okay? So my claim is the size of the vertex cover is always greater than the size of the matching or the same. Okay. In other words, the size of M is upper bounded by the size of the vertex cover. Okay, so it is at most the size of the vertex cover. Okay. So this is the message that I want to convey, that the size of matching is at most the size of the vertex cover. Okay. And the reason that I want to use this claim is that suppose I have a matching and I can show you that the size of the matching equals the size of some vertex cover. Then this is a certificate to show that this is the best you can do. You cannot find a larger matching. Okay? So that's why I want to discuss this claim. Okay? Okay, but back to this claim itself. So why is this true? Why is that you can never find a matching that is larger than a vertex cover? 我们这边讲就是任何一个 matching 跟任何一个 vertex cover，OK？、所以我刚刚最前面一开始我有讲到一个问题是说，如果你的 matching 是你已经算出来了 ，OK？ 你觉得是最大的 matching， 但你要某种程度要说服别人说你的 matching 是最大的，那你要怎么说服别人 ？OK？ 那我们刚刚前面的方法都是，譬如说假设这整个 graph 就是100个点，那我这个 matching 就已经可以 saturate 100个点，那当然是最大。但有时候这不会是那么刚好 ，OK？ 所以我们这边说的是，事实上所有的 matching， 它最大就是 vertex cover 的大小 ，OK？ 那如果我今天手上有一个 matching， 然后我同时也给你一个 vertex cover， 然后我跟你说，我的 matching 跟我的 vertex cover 是一样大，那这个就代表说我手上的这个 matching 就一定是最大，你不可能找到一个比我手上的 matching 更大的 ，OK？ 因为这样它就会违反这个 claim。OK， 所以这为什么这个 claim 是对我们来讲是重要的 ？OK。Okay, so the proof is not difficult. Okay, it's like it takes just 1 or 2 lines. Okay. 所以为什么 vertex cover 大小一定会比 matching 更大？或至少是一样大。Okay, suppose this is your matching, and it has 5 edges. Okay, so here we want to show that any vertex cover must contain 5 vertices. It cannot use just like 4 vertices. Okay, and then we're done. Okay, that's the goal of the claim, to show that the number of vertices we need to cover all the edges in the graph is at least the size of the matching. So let's forget about like to cover all the edges in the graph, okay? Let's just focus on cover all the edges in the matching. So if you want to cover these 5 edges, how many vertices do you need? 如果你忘掉什么，你要 cover 所有的 graph 里面的边，你只是需要 cover 这个 matching 里面的边，这样你至少需要几个边啊？至少需要几个点？5. And the reason is that for edges in the matching, they cannot share endpoints. Okay? They cannot touch each other. So if you want to cover 2 edges in the matching, you must use at least 2 vertices. You cannot just use one vertex to cover multiple edges in the matching. Okay? So if you have 5 edges in the matching, you have to use 5 vertices. Okay? And that's just to cover the matchings, okay? Just to cover the edges in the matching, okay? We also have to cover edges that are not in the matching. So, yeah, we have to use at least this number of vertices, okay? So because edges in M, they do not share endpoints, therefore we need to use at least M vertices just to cover the matching. And that's basically the proof, okay? Okay. So the plan is that when I got a matching, and I believe that this is a maximum matching, right? Then I will also construct a vertex cover such that the size of the vertex cover equals the size of the matching. And according to the claim, the matching will be the maximum matching. Okay? So this is the plan. Okay? So the plan works for bipolar graphs, which I'll discuss next week. But today I want to show you that the plan will fail if it is a non-bipolar graph. Okay. So for example, this is not a bipolar graph, or if you want, you can try like just a triangle. Okay. We already mentioned that this is not a bipolar graph. Okay. So the size of the minimum vertex cover So what is the size of the minimum vertex cover? If you want to cover these 3 edges, how many vertices do you need at least? Can you cover 3 vertices using just 1 vertex? No? Okay. You cannot do it by using just 1 vertex. You have to use 2. Okay? And what is the size of the maximum matching? So what's the largest matching you can find? 1, just 1 edge, okay? You cannot do 2, okay? So 1. So if the graph is not a bipolar graph, then the smallest vertex cover will be, the size will be greater than the size of the matching. Okay, so the plan fails if it is not a biparallel graph. Okay, but the good news is that if the graph is biparallel graphs, I think that's part of the reason that we discussed biparallel graph. If the graph is biparallel graph, then the smallest vertex cover would have a size that equals the size of the maximum edge. Okay. All right. So we're going to discuss that next week. Okay. And also next week we're going to discuss the solution for assignment 1. Okay. So I'm going to upload the first assignment to Moodle tonight. Okay. All right. So that's it.